All right. So when we're talking about the number system, we deal a lot in real numbers, right? And we've talked about like we have the natural numbers, which are like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Like that's what the natural numbers are. The natural numbers go from 1, 2, 3, forever and ever, right? And then above that, we have the whole numbers, which is same as the natural numbers, right? But we start counting at 0 instead of 1, right? And then above that, we have the integers, which we call z because I don't know, which is the same as the whole numbers, right? Except for that we have the opposites. We have all those negative numbers too. So we have every whole number plus its opposite, right? So we've got forever to like -1, negative, well, 0, 1, 2, forever and ever and ever, right? And then on top of that, we have the rational numbers, which we call Q, right? Because of quotient. That one I know why. And that's anything. I'm just going to put fractions. Not even going to write them. I'm just going to all the same stuff, but also fractions, right? And all of these, and then also we have the irrational numbers like pi and e and the square root of 2, right? So we have our irrational numbers that would fall into what we call the real, right? This is the real number system. And over here we'd have our irrational numbers, which are like pi, square root of 2, square root of 5, all those numbers that don't fit in any distinct spot on the number line. Like we can narrow them down, but we're never going to get to the like exact point of them because they kind of go on forever and ever, right? Then all of this is all the real number system. And the real number system sits inside what we call the complex number system, right? And they make a little thing like that, and it's for complex. But what we have in here is we have our pure imaginary numbers, like anything I, we call it a I because it can be I and anything times I. And then we also have our a plus bi, which is real numbers plus an imaginary component, right? So the real numbers sit inside this complex number system. But there's not a lot to the complex number system. There's just like three main pieces of information you need to know. And they all really deal with the letter I, that little imaginary bit. And that is when mathematicians were mathing back in the early days, they needed to be able to take the square root of negative numbers, right? Because what do we know when we're dealing in the real number system? If I look at, say, the square root of -1, we kind of get frozen on that, right? Because if I multiply 1 times 1, I get 1. And if I multiply -1 times -1, I still get 1. So there's really nothing that multiplies times itself that's going to give me a negative number. And that's what a square root is, right? So if I had, say, a problem like x squared equals -1 and I need to solve for x, right? When I take the square root of both sides, I'm at a loss, right? Because I get x here, but the square root of -1 doesn't equal anything. And we decided as a mathematical society, they actually didn't ask me about it. They just kind of decided it long before I was born, that we would make the square root of -1 equal to I. So what it allows us to do is it allows us to pull the negative out of all of those square roots, right? So the square root of -1 equals I. Another, oh, I should say, this doesn't equal I. Yeah, it does. So what we're saying is the square root of -1 equals I. We have also decided that I squared would equal -1. So these are the two most important pieces of information. Because otherwise, anytime you're looking at an I, an imaginary number, you're just going to deal with it like you would any other variable, right? The only difference is when you get an I squared, it's going to become -1. You're going to replace it with -1. That's literally the most complex part, the most important bit to remember is that the square root of -1 equals I, and that I squared equals -1, right? Now, I was telling you before that like when we're talking about complex numbers, we've got this other component, right? This A plus BI unit, and it's how we deal with real numbers and their imaginary components, right? And so when we're talking about like adding and subtracting and multiplying and dividing these complex numbers, we need to know like the standard form of how they would be written. I'm just making sure I'm looking at all of my notes correctly. And so that's what we're talking about today. We're just going to talk about the easier operations on complex numbers. What is the standard form? How do we add, subtract, and multiply and divide these numbers? And in a way, you already know how to do it, right? Because we just treat it that I like it's a variable unless we get an I squared, in which case then it becomes a little more complicated because we got to make it -1. But let's just do it in terms of examples, and we'll start with addition and subtraction, and then we will move on. But the main thing that we need to know is that the standard form for imaginary numbers is this A plus B I. Your real component and plus or minus your imaginary component. Okay, so when you're putting them in order, if you put them in the wrong order in WebAssign, the reason I'm hammering this in is I don't know if it'll give you the right answer if you don't have it in the standard form. So, and we'll see this better when we're talking about it in terms of actual problems, but I just wanted to make that clear before we got going. You have your real component plus or minus your imaginary component. So let's look at problems. When we're talking about adding our sums, right? If I have A plus BI plus, this is just the standard form right off here, C plus DI, we can rewrite that as our imaginary parts added together. So A plus C plus B plus DI, right? Means you're going to add those numbers together just like you would if it was a variable. Same thing if we were talking about the difference, right? If we had difference or subtraction is difference. If I had an A plus BI plus, oops, sorry, minus, saying subtraction and I'm doing addition. A plus BI minus C plus DI, that is going to equal A minus C plus B minus DI. Now, those are your standard forms of writing them out, but let's talk about that in terms of actual problems, right? Let's do some examples. So if I have, for example, 4 plus 7i plus 1 minus 6i, when I rewrite this, like really, the parentheses don't mean anything because in between the two of them, it's plus, right? So if I wanted to, I could write this as 4 plus 7i plus 1 minus 6i, and we could just combine like terms as though those i's were just variables, right? The only difference is normally when we have a variable, we write it first, and when we're dealing with imaginary numbers, we write it last. So I'd go, well, I've got 4 plus 1 here, that's 5. 7i minus 6i is plus 1i, which we would just call I. Not too difficult, right? But if I have that same, well, if I have a similar problem and between them is a subtraction issue, so say I have, that's just giving me two, oh, there we go. I just didn't like this one because it gives me an extra component. If I have 3i minus negative 2 plus 3i minus 2 plus 5i, we can rewrite this. We just have to distribute those negatives through, right? So this 3i right now would stay the same, right? But here I have minus minus 2. Well, that becomes plus 2 minus 3i, right? And we've taken care of that whole thing, but I have to distribute this negative as well. So that becomes minus 2 minus 5i. And now you can just combine all your like terms, right? This is the same thing that we would do if we were just dealing with an x variable at this point, right? We're not doing anything like magical here. When we're adding and subtracting, for the most part, our i's are always just going to stay i's and they're going to be treated like any other variable. It isn't really until we get into the multiplication that we start dealing with I squared and creating that negative. So now we just look at our numbers, right? We got 2 minus 2, well, that's 0, right? So I don't have any real number component, right? Because they zero out. Here I have 3i minus 3i, well, that's 0. But then we have minus this negative 5i, which is just going to give us negative 5i when we're done. Does that make some sense to you guys? Like it's really just being treated like any other variable. We're just kind of getting a little more intricate in our details. Like if I have a problem, one thing to remember is it's only a difference problem if the negative comes in between or before a parentheses, right? Because it's the only time we have to treat it any differently. It's the only time we have to distribute that negative. If I have the problem, three plus 2i plus 4 minus I minus, minus 7 plus I, right? We got a lot going on here, right? And if I wanted to, like if I looked at each component, I could break it down and I could make like one that's 3 plus 4 minus 7 and then have another one. But I think it's easier to just think of it in terms of, okay, here I have 3 plus 2i. It's all added, so I don't have to worry about any of that. Nothing, there's no negative on the outside here, so I could call this plus 4 minus I. But this negative, I got to distribute. So this becomes minus 7 minus I. And now I can combine all of my like terms again. We're going to do our real components first. 3 plus 4 is 7. Ooh, 7 minus 7, that's 0. Then I've got 2I minus I, well, that's 1I, minus another I, well, that's 0. So that would be like plus 0I. So the whole thing is just 0. Right? Will it always work out like that? No. But I kind of want you to see how like those components are going to be different, right? Let's see what I got there for you. I feel like that's a pretty good example of adding and subtracting. I'm not going to go over properties with you because I'm not going to assign you anything on properties. Multiplying. When we're multiplying, let's see if I can make that scan up for me without making a mark on the screen. Now, when we're multiplying, we're going to use a lot of distribution, right? So, for example, everything still like will FOIL or distribute, just like you're multiplying anytime you have variables. It's going to work the same way. The difference is sometimes you're going to get these squares, right, on your I, and you're going to have to make that square -1 and then find your solution from there. So say I have 4 times -2 plus 3I, right? I'm going to have to distribute that 4 through each piece. So 4 times 2 is -8. 4 times 3 is plus 12I. And that's as good as that is going to get, right? We don't have an I squared on this problem, so this is our final solution. But say I have 2 minus I times 4 plus 3I. Now we have to do that FOIL method, even though I hate the term FOIL because it only works for binomials. We're going to take our 2 and we're going to multiply it times 4 and we're going to get 8. And then we're going to multiply our 2 times 3i. Well, that's going to be plus 6i. And then I'm going to take this, right? I'm going to go -1 times I, and that's going to give me -4i. And then I've got -I times 3i, and I am going to get -3i squared, right? All that I squared is going to do is that becomes -1. So all it really does is change that sign to a plus, right? And I'm going to show you how in a sense right now. So if I have 8 plus, well, I've got 6i minus 4i, so we'll call that plus 2i. And I have minus 3i squared. Well, that's minus 3 times -1. And so that's the same as saying 8 plus 2i plus 3, right? Because -1 times -3 just gives me plus 3. And we can rewrite this now as 11 plus 2i. Does that make sense? I got some head nods there. So, and I'm trying to see if I've got anything more complex to show you, but that's really as bad as it gets for the most part. Sometimes you'll get your stuff written as 4 plus, say, 2i, and that whole thing is squared. But that's really just saying 4 plus 2i times 4 plus 2i, right? And you can work that out. What's nice about that is like there's a pattern. Like if you know the pattern, then you could do it right away. But even if you don't, all you have to do is multiply it out, right? You got 4 times 4 is 16. 4 times 2i is plus 8i, and then we've got 2i times 4, which is plus 8i. And then you have 2i times 2i, which is plus 4i squared, right? So you have 16 plus 16i minus 4, right? Because 4 times I squared is just minus 4. And so you wind up with 12 plus 16i. I should be putting in my equal signs each time, but I got lazy. It's been a long day. So really not super complicated, because it's still the only thing that changes when you're multiplying is if you happen to wind up with a square on your I variable, just change it to -1. Everything else makes it play like a variable, right? Little trick for you when you're dealing with complex numbers. I know I went over this with some of you the last year, right? Think about this. If I have I times I, right? That's I squared, and we know it's going to be a negative, right? It'll be -1. What if I have I times I times I? If I have I cubed, what's that going to be? Well, it's like taking this -1, right, and multiplying it times I. So it would be -I. What if I have I times I times I times I? Well, that's I to the 4th, right? Well, that's like taking this -I and multiplying it times I. So I get negative I squared, which just brings me back to I. Right? Because if I plug in -1 for that I squared and I multiply it times the negative, it's just going to make it positive. So there's only three things, right? 4 things that it could be. So I is just I squared is -1. And then we've got I cubed is negative I. And then we go back to, oh no, it's 1, and then we have -I. Right? So there's only so many things that it can be. Right? That's me being tired. But I'll show you how that works out next time I see you, because I want to get to division so that we can go. Division's the easiest thing that we will be dealing with. Multiplying conjugates. I don't want to talk about that today. Talking about the complex conjugate. I'm not going to go into that today. Quotient of complex numbers. You know what? I think we're good for today. We're just going to be doing adding, subtracting, and multiplying for today. Because the rest of the stuff gets more complex, and I don't feel like getting into it. I don't feel like getting into it just yet. So I'm just going to give you some problems dealing with that, play around with it, and then we'll finish this off next week in the beginning. This is the only section we're doing from chapter 2, is this complex number section, just as a reminder. And then we're going to hit a little bit on exponential stuff and logarithms, but at this point none of this will be tested. It's just going to be homework, because we're just kind of filling in some gaps. We don't have time to do an entire unit before the end of the semester, because I don't want to take time to give you guys like a test, and we're not going to do a final. We have like what, all of next week. I'm going to stop recording.